First, I sincerely apologize for yesterday, meaning acceptance and apology, and God willing, we will indeed make up for it today or tomorrow, God willing. Thank you, doctor. Thank you, doctor. So, God willing, as we continue, are there any issues regarding the last two lectures on nuclear imaging?
All right, sir. Thank you, God. Okay, that's great.
Okay, doctors, I won't talk about what has passed, but we will start, God willing, to continue. We talked in the previous lectures about the basics of nuclear imaging. We discussed the gamma camera, the types of collimators, and we talked about the photomultiplier tube. We even discussed how the crystal works to produce the final image. We talked about how, in the end, I have an image that comes out, meaning the idea of the final output. There are some details that we will discuss regarding the gamma camera itself, such as the types of scans it uses. For example, we know that we need to perform an X-ray, such as taking an AP image, a BA image, and a lateral image. The same can be done with the gamma camera. If you want to take an image similar to a CT scan, you can take a volume and then perform reconstruction for axial, coronal, and sagittal views. This can also be done with the gamma camera for tomographic imaging, as we will discuss shortly. There are examinations that depend on taking dynamic scans, like in X-ray, where you can perform a dynamic examination by injecting a contrast agent and taking several images in quick succession, observing each image in 1 second or less, and seeing the changes in the uptake of the radiopharmaceutical in the specific organ. For example, when we talk about the contrast from the kidney, if we are doing something like videography or an IVP, there are examinations that can be performed dynamically. The same idea applies to nuclear imaging, where there is also a dynamic examination, but instead of discussing contrast media, we are talking about radioactive material. We want to observe its entry and exit from the organ, so I also refer to this examination as dynamic. Well, you also have an ST test, for example, where you perform cardiac imaging, you connect the ECG, and observe the coronary arteries. Additionally, if you have software processing like the one used for ejection fraction, you can derive the ejection fraction from it. The same concept applies to the gamma camera. Or SPECT, you can do the same thing and also perform gated imaging. However, here you are dealing with radiopharmaceuticals, and there is a significant similarity between the different imaging modalities, but what creates contrast in the images varies. For instance, if I have a patient and that patient has different objects in this manner, various types of electronic devices are available in the market today, each serving different purposes. And in different places, that's it. And it can also have different sizes. And also the uptake of the radiopharmaceutical and the concentration of the radiopharmaceutical can vary. They are not always equal. For example, you might find that the radiopharmaceutical is concentrated more in the heart than in the kidneys, or vice versa, depending on the radiopharmaceutical you are working with. So if we assume that this part here is the counts for me, and let's assume that this part, which contains the radiopharmaceutical, is what we often refer to as a term. What does that mean? We say the term, what does it mean? Dr. Islam, can I hear you? Are you referring to the screen? Yes? Is it a phenomenon with you? No, it's not a phenomenon. Okay, I'm sorry, I apologize. Okay, good, I caught up with you. May God bless you, thank you much. Oh no, it's fine, doctor, so there will be a continuous repetition. I read well. So right now, for example, I have, let's say, 3 patients present, and there are different ones. Currently, I am handling a situation where I have, let's say, 3 patients who are present with me at this moment. Each of these patients is different from the others in various ways. So when I say, it means that I have, for example, this. Therefore, when I mention this, it signifies that I have, for instance, this particular scenario. This is the situation for me. There are some megabecquerels or some millicuries. We said that there are 2 units. You are talking about curies or megabecquerels per milliliter. So I call this concentration activity. When you talk about a radioactive substance inside the patient, you are talking about concentration activity in megabecquerels per milliliter. When you talk about the image, your image consists of pixels, so you are talking about counts per pixel. How many counts per pixel are present here? This square will appear in the image as a square, but in this segment, you are asking about the counts per pixel. Now, let's go back to the point. I want to discuss honestly, right now I have this square here with high activity, so I expect that the number of photons emitted from it is a lot, not just a little. It's a lot. Really great. It's nice that the number of photons coming out here is large compared to the circular one, which has low counts, meaning it has low activity or concentration activity. So the photon coming out will have a low number here. All right, the triangle, for example, we can say is in between the two. It has a different color, like yellow-green, for instance. In this process, we are going to undertake a detailed reapproximation of the photons that are emitted from the source. This involves a comprehensive analysis and recalibration of the photon emissions, specifically focusing on those that are released in the half. By doing so, we aim to achieve a more accurate representation and understanding of the photon behavior and characteristics. This step is crucial for enhancing our overall comprehension of the emission patterns and their implications in the broader context of our study. What do you think your image will look like? Will the image show the shapes? Perhaps even a variety of different shapes and forms? So, do you expect to see a square, a circular shape, or maybe a triangle in it? It will be like you're seeing, the television picture at your place back in the day. This generation, when you had a television that would turn off, or there was no signal, what did you see? You saw a picture with nothing but white dots filling the whole image. This is what you will see if the collimator is not present. Why? As Dr. Hani said, I have photons, folks, moving in all directions. This is not just a photon going towards the collimator. You might find one like this. No one like this, no one like that, no one like this, no one like that. This is going in a way that consequently the crystal for you cannot determine precisely where this photon is coming from. So when you come to do localization and determine the X and Y, positioning with the XYZ circuit, we talked about last time, the location is coming in the Tor area. I don't know. That's why the topic of the collimator came up. So what did the collimator do for you? It said, I will draw like the grid we were talking about, and there are strips of lead, and there are holes. These holes only allow the photon coming perpendicularly to pass through. So that's what gets through and reaches the crystal. So what will you benefit from this? I will benefit, well, that the photon for me, the photon coming in perpendicularly to the hole will interact at a specific point on the crystal. When this interaction occurs at that particular point on the crystal, it leads to excitation and releases an electron. The structure of the crystal, as we discussed in previous lectures, includes something called the valence band and the conduction band. The scintillation occurs, and the electron moves to the conduction band and then drops back to the valence band, emitting light. The emitted light can be, for example, around 5,000. Keep in mind that every time a photon comes out, it hits the same spot. You can imagine that I am not just taking a single measurement, I am continuously counting. Every fraction of a second, a photon is emitted because the emission process of the gamma photon is ongoing. Consequently, what happens is that the emitted light goes out in all directions. It is important to note that this process is continuous and ongoing, meaning that the emission of photons and the subsequent release of light is a constant and unending cycle. Furthermore, the interaction of photons with the crystal is a critical aspect of this process, as it determines the efficiency and effectiveness of the light emission. In conclusion, the entire mechanism is a fascinating interplay of physics and chemistry, resulting in the beautiful phenomenon of light emission. I want to receive it. How do I receive it? Do I need to have a photomultiplier or a photocathode? What is the photocathode? The photocathode will convert the light photon into an electron so that later I can work with this electron, perform multiplication on it, and convert it into a signal. This signal can then be translated into an image. Now, there is a problem. The crystal, I want you to imagine with it. Excuse me, doctors, just a second. I'm sorry, just a second, but the kids, just a second, I'm sorry. I'm sorry, doctors, for the interruption. Let's go back. We were at the point where I have a light photon that I want to receive. I want you to imagine with me that this crystal is like your image. And what are you doing with a map? This map, or the crystal itself, represents what? Above the patient, it encompasses all dimensions of the image or the field of view that you are imaging. At every point of the patient, a gamma photon is interacting above it on the crystal. Therefore, the crystal here acts as if it represents the interactions or the locations of the gamma photons that are actually inside the patient. Can you imagine this, doctor? All right. Should I continue? Can I have another second, doctor, please? Again, I mean, here is the patient, right? This patient emits gamma photons, right? These gamma photons hit the crystal. Here is the crystal. The crystal, the collimator, and the photomultiplier tube are all involved with this photon that passed through, which is the green line. It created scintillation in this position. Now pay attention. The crystal itself has dimensions. It has a certain depth and has an XY dimension, meaning it corresponds to the length of the patient's body. So, when we came to take the images, we talked about look, doctors, here is the crystal. For me, the crystal itself has a dimension, meaning it has this dimension that you see here. This is under the crystal. So every point here corresponds to a point in each point on the patient's body corresponds to a specific point on the crystal. So you can think of the crystal as representing your image, and the locations of interactions can be clarified a bit more. This is clear to you, and this is the collimator, and this is the patient, and this is the hole, or this is the collimator. Each hole corresponds to a specific location and point on the patient. Therefore, this interaction occurs at a specific point on the crystal, and thus the image produced essentially determines the locations on the crystal. These locations represent the emission point of the photon in the patient's body. Can you visualize this, or should I repeat it? This is critical. This is a square shape of the collimator, and this crystal is for me. Therefore, there is a photon emitted from here and a photon emitted from there. Each point has a gamma photon coming out of it. Of course, there is also an internal direction, as if you are moving in that direction. The same idea applies. Consider it a square that covers the patient in the X and Y dimensions for me. All right, the crystal where scintillation occurs. The previous image shows you that if you don't have a collimator, then of course the interactions occur in all directions, resulting in a distorted image, as we were also discussing here. This is the idea of scintillation that occurs when the valence band and the conduction band release an electron, which then falls back into the valence band and gives you the light photon. This is what happens in scintillation. Now come here so you can focus with me. In the photomultiplier tube, you will find that every point where interaction occurs happens at each point. This point above it in the photomultiplier tubes on the surface of the photocathode start telling you what the point is, which is the scintillation point. It wants to determine the location of the scintillation on the crystal so that it can know the exact location on the patient's body from which the gamma photon is emitted. How does it do this? Simply put, we know that the light photon travels at the speed of light, which is 3.10^8 meters per second, a constant speed for me. Now, how can I obtain the time? Because every difference of a second, a photon comes to you from this location. You can know which signal came to you first, or if another signal came to you. So how can you know the time or the time it takes for your signal to reach you? For example, if this signal came to you 1 second after the first signal, then the time it takes for the signal is 1 second for it to reach you. All right, so we know that the equation stating distance equals speed divided by time can determine the location of what happened. This could be, for example, between 4 in this shape or close to a photomultiplier tube, or perhaps focused on one of the photomultiplier tubes. For him, every photomultiplier tube that receives a signal starts calculating the distance here, the distance here, the distance here, and the distance that reached here. Then, using a specific equation and certain calculations, he begins to determine the location of the scintillation. In the end, he will have a map on the crystal itself that shows you the areas where scintillation occurred, which represent the points coming from the gamma photons emitted from the patient's body. All right, now the point is, after the interaction occurs, pay attention to the patient's body. If I am talking about this patient, it is technetium with an energy of 140 kiloelectron volts, meaning the energy of the gamma photon emitted is 140 kiloelectron volts. The radioactive material is emitted from the patient first. Before I discuss this part, do you remember the topic I was talking about a little while ago? You expect this square part to be essentially the signal that reached the crystal with high counts and low counts. He will know that this problem or 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 this problem, you wrote from the hecons that it has a detection function on the crystal, and it takes counts that will give a signal, but much less. The medium will give a signal, but in any case, this is number one. This is his map. He can know from it several things. First, the counts per second give him the strength of the signal, or the signal that came to him, or the activity concentration present inside the object, which gives him this number one. So, I must take care that I have a collimator. This collimator, doctors, is supposed to allow the crystal to perform higher detection if I remove the collimator. Whether in the absence of the collimator or in the presence of the collimator, if you remove the collimator, the crystal can detect many counts or fewer. It's a lot because the collimator acts like a grid, doctors, meaning that there is an LED, which consequently reduces any incoming photon at an angle that will undergo absorption in the existing strips. So it reduces what is called sensitivity of your crystal. This means that the presence of the collimator decreases the counts per second, which affects the activity. For example, if I say I injected this patient with a megabecquerel, what would your crystal detect in terms of counts per second or counts per minute for each megabecquerel administered to the patient? Give the patient 1 megabecquerel. Look at the crystal. It will count counts per second at that moment. Its presence reduces the counts that you will measure in the same minute for the same activity. So, the counts per minute or the counts bare activity. This is what I call sensitivity. When I talk about collimators, I had a low energy collimator or a low energy all-purpose collimator and a low energy high resolution collimator. We had high energy and medium energy. So, we used to say, what is the difference, doctors? We used to say that when you mention the low energy collimator, its thickness is small or large. What do you think about the thickness? This is about the collimator that is fixed, which is the LED. Do you remember I was saying that in order to measure energy, in the calorimeter, the photon that falls on the hole has low energy. This low energy means you don't need a large thickness of the substrate to stop the low energy. Therefore, the thickness is small. Okay? If the thickness is small, what does that mean? It means that you will find that the hole for you becomes significant. The sensitivity is higher for low energy compared to high energy. Why? Because the thickness of the substrate will increase. As the energy of the photon increases, you need a greater thickness to stop any scattered photons coming at an angle. This will cause the space or the hole's diameter to decrease because you have increased the thickness of the substrate. So, the opening or the hole through which the photon passes has become smaller. When the opening decreases, the number of photons passing through the hole will decrease, which means sensitivity decreases, right? Therefore, the diameter of the hole is very important when comparing low energy, high energy, and medium energy based on the hole and the substrate thickness. This affects your sensitivity and also affects what? The resolution. When you want to increase the resolution, what do? For example, General Alberbus, who considers this lens, has a short hole lens, not very large, and the thickness of the substrate is low. If you want to achieve high resolution in a calorimeter, what should you do? There is a calorimeter called low energy high resolution, which has the same thickness of the substrate, but it aims to provide higher resolution. So what does it do? It increases the length of the opening. When you increase the length, what does that mean? It reduces the angle from which it can receive photons coming from the source. Now, for ultra high resolution like this, the length is significantly increased. thus the length of the hole and the diameter, along with the thickness, are three factors that affect resolution and sensitivity. If you want to increase resolution, increase the length and reduce the diameter and the thickness of the substrate. However, keep in mind that when you increase the length, reduce the diameter, and increase the thickness, you have indeed increased the resolution. But who has decreased the sensitivity, doctor? This is always the problem. The problem is always in nuclear imaging that you have to balance between resolution and sensitivity. That's why they tell you that the target is to achieve the best resolution and optimum sensitivity. This is the goal for me, and consequently, they find ways to overcome this issue.